Hello everyone, Mr. John here from Areteem Institute with this week's video following up last week's video. I would really recommend you check that video out. It's linked in the description below, where we're going to talk a little bit more about this new proof of the Pythagorean theorem and talk about trigonometric proofs there a little bit. Quick review. Pythagorean theorem most people are comfortable with. In a right triangle, a squared plus b squared equals c squared, where we have the sides and the hypotenuse in that case, right? Two high school students recently presented a new proof of the Pythagorean theorem, or I think a couple of proofs using trigonometry. This was once thought impossible. Right? Check out that previous video for a little bit more information there. We're going to focus on a couple of our questions from last time in this week's video. First question was, use the Pythagorean theorem to prove the law of cosines. Now, this is the usual way things go. When you learn about the law of cosines, right, or you learn about trigonometry, you typically start with the Pythagorean theorem and then go forward. So that's the basic idea behind why people might have thought that there's no trigonometric proof of the Pythagorean theorem. We proved, of course, last time the law of cosines proves the Pythagorean theorem, and it's easy to get into these circular reasoning things. So when we're doing this proof, right, we want to make sure we're kind of talking about why there are no circular reasonings in that way. Right, of course, you can prove the Pythagorean theorem using no trigonometry. That's kind of what we're assuming here. And so we'll talk a little bit about some steps we maybe could be a little worried about there. But we'll explain why no circular reasoning is taking place. And this is the straightforward way to move from basic stuff like the Pythagorean theorem to trigonometry to law of sines and cosines, things like that there. So, quick reminder of the law of cosines. We want to prove that c squared equals a squared plus b squared minus 2ab cosine c. And the proof idea here, the proof will take a little bit longer, but the proof idea is very, very simple for something like this. If we have a triangle and we have three sides, so let's say c squared, c here, a here, b at the bottom, or actually let's make b here and a at the bottom in this case. And just for a little simplicity in this setup here, let me just refer to angle C, right? So that's the angle opposite that side C. Let's just call this theta for our purposes. So we can call this angle here theta in this scenario. Now, the proof idea here is very, very simple. Anytime you have a triangle, right? It's not a right triangle, general triangle. Maybe you need to shift stuff around a little bit, but the rough idea is let's draw in an altitude in this scenario there. So let's draw in this altitude. I'm going to call the height h in this scenario. And now notice we've broken down the triangle or the side A into two pieces. So let me call one of those pieces x, and then the other one is, of course, a minus x, because they add up to the a side there. Now, remember, we're using the Pythagorean theorem to prove this. And so let's start thinking about Pythagorean theorem type statements. So if we start looking at some Pythagorean theorem type statements, well, what if we look at c squared? C is the hypotenuse of this triangle there with one side h. So we have a h squared plus a minus x squared. So let me just kind of maybe star this with kind of this portion here. Let me maybe underline it, right? This portion is, again, the Pythagorean theorem for this triangle right here. No trigonometry, right? Everything's pretty straightforward there. Now, natural thing here is to start expanding some stuff out. So we have h squared plus a squared. And let me reverse this, right? Of course, actually, a minus x is the same as x minus a. You'll see in just a moment why I'm kind of rewriting this the opposite way, right? We can say x squared minus 2ax plus a squared there, right? The reason for this is, of course, that we see h squared plus x squared, right? So, hey, that is another right triangle type thing. And in fact, that shows up in this triangle here where B is the hypotenuse. So let me write it out, rearrange stuff a little bit there. That is then B squared plus A squared. So we're looking good so far. And then we have the 2AX there. Now, our final question is about theta, right? And X. We have this theta in the formula, cosine of C. The only thing that doesn't look like the equation we have so far is dealing with X. And so let's think about a second there, right? What about that theta? Can we write an expression about theta involving X? Well, sure, right? Note that cosine of theta is actually x over b. And if you think about this a little bit, this is exactly what we need, right? X here then is b times cosine of theta. And if we plug this into our expression, we are done, right? We have, and let me just clean this up so it matches perfectly, a squared plus b squared minus 2ax, but x is b cosine of theta. So everything looks good. We have a proof there in this scenario. Now, it's not super relevant here, but just to preview some things we're going to talk about in a second, you might be a little worried, are we doing anything circular here? Not really. What I want to point out is, and it's pretty safe in these scenarios when you're using right triangle trigonometry. That I'm going to say again in a moment. This is a right triangle. Cosine of theta can be defined, right, as the adjacent over the hypotenuse. We're not doing any unit circle stuff. Very, very basic initial definitions there. Want to stress that because that will be important in a little bit as well. Now, right, we introduced this idea last time that there's actually some trig proofs floating around. So these high school students weren't the first ones to come up with trig proofs. They did, by all accounts, come up with new proofs. It's still a great result there. But, right, there was a proof in 2009, at least a paper, right, using this cosine difference formula as the base, right? We're going to need a little bit more, which I'll talk about in a second, but that's the base idea for this trigonometric proof of the Pythagorean theorem. Now, right, what is the idea of this proof? So it's going to be two steps. We're going to do the steps in reverse order. So the first step is using the cosine difference formula, actually sine difference formula there as well. They're very similar. Prove that we actually have this trig identity, cosine squared plus sine squared equals 1, right? Notice that typically speaking, this would just be Pythagorean theorem. If we do unit circle trigonometry, this is built into the definitions there, right? So we're not assuming that. We need to prove that here. It's not too hard to say that that proves the Pythagorean theorem there. And, right, I'll point out along the way some things we need to be careful with. In particular, this goes back to what I was saying before. We want to focus on, and we're not going to talk about all of the details there. These things are happening for right triangle trigonometry. There's no unit circle. We're doing this for angles between 0 and 90 degrees, things like that there. So let's, like I said, do this in kind of the backwards order here, just to motivate where this cosine squared plus sine squared equals 1. Right? So yeah, c squared plus s squared here is cosine squared plus sine squared equals 1. Now, how can we use that to prove the Pythagorean theorem? Well, if we have any right triangle, right? We have a right triangle here. We have a hypotenuse C, right? Sides A and B, and some angle X or theta here, right? If we know that cosine of X squared, right? So cosine squared of X plus sine squared of X equals 1. Again, just right triangle trig. What is right triangle trig telling us, right? Then we have that, well, cosine of X is actually just, right? That is just going to be equal to A over C. So we actually have A over C squared plus B over C squared. And right, rearranging this, we get A squared plus B squared equals C squared. So this is very trivial, right? This is typically, if you're doing a math class in advanced high school or college, this would be the scenario of when you got to this point in the proof, that's left as an exercise, right? But we did it here. It's pretty simple to say if you can prove cosine squared plus sine squared is 1, then we can prove the Pythagorean theorem. And again, if we're doing this in a right triangle, we know x is between 0 and 90. So we can focus on those angles. We can focus on basic right triangle trigonometry. Now, let's look at how we can prove this with the sum and difference formulas here. Now, just doing a little bit of kind of explanation of what would be going on with the full proof behind the scenes, right? These you need to prove. We're not proving these here, but there is some work to talk about this and be careful what you mean by that there. Remember, we're focused on angles between 0 and 90 degrees. So when we're doing this, our assumptions here are that if we're looking at these differences and looking at combining these angles, both A and B are between 0 and 90, but also B is less than A. There's no negative angles. You're proving these with the difference angles there, so everything is a positive angle between 0 and 90. There is some work that needs to be done there behind the scenes, but that's the key for the no circular reasoning. Typically, when we learn these formulas, we learn them after we do unit circle trigonometry. That's reliant on the Pythagorean theorem. So kind of we need to go back to the basics, and that's why it is important that we need to prove stuff there. But with those proven, this becomes another kind of algebraic manipulation type of thing. And these kind of tricks are a little bit funny sometimes when you see them, but they do show up in different places of mathematics along the way, right? You can do a lot with nice substitutions or nice manipulations of known equations. So let's say we have here, and let's look at cosine of A minus A minus B, right? Of course, this is just cosine of B, right? So actually, let me do this and give myself a little bit of room here. So we can say, okay, let's look at this angle cosine of B, and I want to rewrite it in this, at first glance, silly way, where we kind of have it written in a couple of pieces, A minus B. Now, this will be our kind of hardest one here because we have to say, okay, A is A, but now the B value we're substituting in is A minus B there, right? So this gets a little bit complicated with the formula and the overuse of the same variables in this scenario, but that's okay, right? We can power through this there. So if we write this out then, what do we get? Well, we get cosine of the pink angle. So we get cosine of A, and then we have times cosine of B. So that is the orange angle, so A minus B. And then we have plus sine of the pink, and then sine of the orange, right? So that one is our A minus B in that scenario. Right, and so in the question, when we said we start with this cosine difference formula, this is what we mean there, right? We're starting with this A minus B trick and going from there. Right, now we have cosine of A minus B, so this is exactly the formula we have. That's why I erased the highlighting there. So we have cosine of A, cosine of B. And let me put the parentheses in just to make sure it's clear, right? Then we have plus our sine of A, sine of B. And right, then we have a similar thing here for the sine difference formula in this scenario as well. So right, then let me move down here, plus sine of A times sine of the difference. So now we have the same type of thing, sine of A, cosine of B. And now, right, our minus, and this minus is going to be very important for what I talk about in a second, cosine of A, sine of B. Okay, now, don't have too much room left here, but that is perfectly fine because some nice things start to happen here. So let's look at kind of combining and distributing the terms here. So in our first setup, we have cosine of A, right? And let me do these on the top. Cosine of A times cosine of A, cosine of B. Let's look at that compared with sine of A times sine of A times cosine of B. If we put those together, notice what we get there is both terms have a cosine of B. This will be important in a second. And then we're left with, right, cosine squared of A plus sine squared of A. So that's what we have there by looking at the first terms distributing these things out. So that's what we have there. Now, what about the second terms? Well, we have cosine of A times sine of A, sine of B. And then we have sine of A times cosine of A, sine of B negative. Notice we have cosine of A, sine of A, sine of B in both places. So those actually cancel out. So we have plus 0. So we actually get that, right, what do we have? We have that cosine of B is equal to cosine of B times cosine of squared A plus sine squared A, right? So we have exactly what we want. If we cancel out the cosines of B's, right, we get that cosine squared plus sine squared is 1 in that scenario. We have what we want in that case, right? Cosine of B, right, isn't 0. We have angles between 0 and 90, so things are good in that scenario here. Okay. Like I said, there's a little bit more going behind the scenes, so let us know if you have any questions in the comments below. Otherwise, that will be a good place to stop this week's video. Subscribe if you like this video. like the video. All of those things really help us out. Otherwise, looking forward to seeing everyone next week. Goodbye.